Okay, so welcome to this next video in which we are looking at synchronous and asynchronous neurotransmitter release. So far what we've seen is that when an action potential arrives in the axon terminal of a neuron, it's going to cause calcium influx, which will cause the release of the docked synaptic vesicles that are in the readily releasable vesicle pool by activating synaptotagmin. Okay? That's called the synchronous release of neurotransmitter. However, few seconds after the the action potential has arrived, you've still got more neurotransmitter being released than you would have just from spontaneous release. So it's like spontaneous release is temporarily upregulated in the aftermath of an action potential. This is what's known as asynchronous neurotransmitter release. Okay, so we're looking at the mechanisms underlying that. We've seen that when calcium goes up in the cytoplasm in response to the action potential, it's going to lead to the activation of this CAM kinase 2, which is going to phosphorylate the synapsin proteins, which will liberate the vesicles that are in the reserve vesicle pool in the axon terminal. These will go to the presynaptic membrane and they will dock. But now the calcium signal has gone down to a very low level by now. So synaptotagmin isn't going to be activated to fuse them. So what instead causes them to fuse? Well, a candidate for this is a protein known as DOCK2. Okay, so DOCK2. Now, DOCK2 basically has 2C2 domains as well, just like synaptotagmin. However, it does not have a membrane-spanning portion. So DOCK2 is a protein that sits in the cytoplasm of cells, basically, and sits in the cytoplasm of the axon terminal with these 2C2 domains, which are capable of binding to calcium. So these are C2 domains. Okay? But it is not bound to the membrane of the synaptic vesicles. Now, DOCK2 is believed to be more calcium sensitive than synaptotagmin. So even at these lower levels of calcium than you would have seen at the peak of the action potential's activity, DOCK2 is still going to be active, even though synaptotagmin has dropped off now. And I want to stress that the calcium level has not yet gone back to the 100 nanomolar level. It's still higher than it would be in the aftermath of the opening of the P, Q, and N type voltage-gated calcium channels, but it's not as high as it was. Okay, now this calcium is going to bind to these two C2 domains of DOCK2, and basically what DOCK2 does is it binds to the snare protein. So let me show you the docked synaptic vesicle. So here's our docked synaptic vesicle. So this is our synaptic vesicle that's come over from the reserve vesicle pool, and it's now docked with the plasma membrane. So here are these core snare complexes that have formed. So synaptobrevin is the V snare, and then the two T snares are syntaxin 1 and SNAP25. So in turquoise here, these two alpha helices contributed by SNAP25, a T snare, and in blue, a single alpha helix supplied by syntaxin 1, okay, and then in orange, a single alpha helix supplied by synaptobrevin 1. So these are these core snare complexes. Now what's going to happen is this activated DOCK2 protein is going to come and bind, and then it's also going to do a similar thing to synaptotagmin. It's going to bind to lipid components of the phospholipid bilayer and cause invagination of the membrane, basically. So that, again, what's going to happen is you're going to fuse the membrane of the synaptic vesicle with the plasma membrane simply because they're brought so close together. And that's going to cause this fusion event here, which is going to lead to the neurotransmitter inside here being exocytosed. So DOCK2 basically is believed to be a candidate for this asynchronous neurotransmitter release, okay, which occurs it's continuing to occur a few seconds even after the action potential has occurred and after you've had a synchronous neurotransmitter release. Okay, but as I say, very little is known about this process. DOC2 is a candidate, we think, for resulting in this increased fusion that occurs in the aftermath of a action potential.